All right. Video solution number 3. It's on question 4. It says, consider the screen coolant potential of a point charge of Q that arises, for example, in plasma physics. It gives it to us. The potential equals Q over 4 pi epsilon naught times e to the negative r over lambda divided by r. And then where lambda is a constant called the screening length. Part A says determine the electric field E of R associated with this potential. So using the relationship E equals negative del V, we can plug in our V here and pull out the constant, and that ends up just becoming the derivative with respect to R of e to the negative r over lambda divided by r. So what that ends up being is negative q over 4 pi epsilon naught times negative e to the negative r over lambda times r minus e to the negative r over lambda over r squared, that quantity times r hat. So then you can just make those all pluses, and that's what our electric field actually is. And then part B says find the charge distribution rho of r that produces this potential, and then sketch the function rho of r that clearly describes its characteristics. Alright, so we have this electric field which we can rewrite in this form. So pulling out an r squared from here, looks like that's what we did, yeah. And the reason we rewrite that is because we can call that term A and this vector B, and we use the relationship del dot E equals rho over epsilon naught. But since we separated into two different things, a scalar and a vector, we can use this relationship. It's a product rule that we have in the cover of our book. And then plugging that into the equation for rho, you get this big, nasty looking thing that actually reduces quite a bit. First off, this part right here, we figured out earlier on in the semester, the del times r hat over r squared reduces to um, 4 pi times the delta function. And what all of this ends up reducing to after all of the simplifying is q times the delta function minus q e to the negative r over lambda over 4 pi r lambda squared. So that's our charge distribution, and then it wants us to graph it, showing its characteristics. So as r is 0, when r is 0, this is the function that dominates, which is the delta function. So it's going to look like a spike there. And then as soon as you get away from that, it ends up being dominated by this, which starts from the negative at negative infinity and comes around. So that's going to end up going like that. So what this is showing is that when r equals 0, so this guy right here, It's an infinitely tall spike, which makes sense because you're at the nucleus, and when R does not equal 0, you're at this part right there, which represents the electron cloud, which as you go further and further out gets thinner and thinner. And if you add up this integral over all space, it's going to end up giving you 0. So then part C says, show by explicit calculation over rho of R that the net charge represented by this distribution is 0. So we have this equation, rho times dV equals Q times the integral of the step function dV minus, what else we had? E to the negative R over lambda over 4 pi R lambda squared. And that's also times dV. But this thing, by definition, that is going to be 1. Then this guy, dV, the volume element, we can just rewrite this as 4 pi R squared times dr, make these cancellations, and then what we're left with is, I'll just write it over here, what we're left with equals Q times the integral from 0 to infinity, well, actually, back, Q times 1 minus the integral from 0 to infinity of e to the negative R over lambda divided times R divided by lambda squared times dr. Looking at this function in particular, we can make this u substitution of R over lambda, then du would equal 1 over lambda dr. Rewriting this, you would get equals Q times 1 minus the integral from 0 to infinity of u e to the negative u du. Now this right here is a gamma function, and by definition that is equal to n factorial, which n is the power of u, which in this case is just 1, equals 1 factorial equals 1. So what we end up having is Q times 1 minus 1, which also is just 0. Alright, so that is my solution.